Hi, and welcome to this section where I would like to continue with our study on regression, and in particular here we would like to see how we can estimate the parameters beta naught and beta 1 if we are given the linear regression y hat equals to beta naught plus beta 1 x1. Okay, so the idea here, if I can take you back a little bit, is that we have here values of y for which we would like to predict the dependent variables, and then here we have the independent variables, and then say we have a set of data points, okay, which we collect, and then we use linear regression to find a line of best fit. Okay, let's assume we have this line, which is that. So we said last time that the idea for this line here, which we are going now to call y hat, of course it is a straight line, so it will follow the equation of a straight line. We can say beta naught plus beta 1 x1. The idea we said here is that we find the line such that all these epsilons here, okay, the epsilons here, the epsilon, any particular epsilon is the difference between the observed value and the predicted. So if we let y, of course here y is the observed value, and then our predicted one is the y hat here, and y hat is the predicted value. So our epsilon here, okay, the error is the difference between the observed and the predicted, any epsilon I. So our idea is that we would like to minimize these errors here, okay. To find the line of best fit, we want to make sure that we minimize this epsilon I. Okay, so we'll minimize that. We shall essentially be minimizing the difference here between the observed and the predicted. Okay, so in what we call the least squares method here, we shall minimize, okay, the sum of the squared residuals. Okay, so that is what we are going to minimize. The reason why we are going to square all these terms is to get rid of the negatives. For instance, here, here, this particular epsilon I, because this is yi and this is yi, and then this is the y hat. So the difference, okay, that is y hat, okay. Okay, maybe. Okay, if now it is maybe this one which is down here, and this is going to be, yeah, the observed, and then the predicted is up. So if we are to take this one in particular, so we would find that yi minus y hat for this particular value here would be a negative, and therefore to get rid of these negatives, we shall have to square these, residuals here, these error terms. So that is, in summary, that is the idea here. So that is what the formula we are going to follow. Okay, the idea, okay, the line of thought which we are going to follow. So that we are going to say that we are going to sum, okay, from all observations, okay, we are going to sum all observations, the particular epsilons, okay, and then we are going to square them. We can denote the epsilon I hat, and then we have seen that, of course, essentially what we are doing, epsilon I is the difference here, yi minus y hat I So we're squaring the left hand side and then also the right hand side. We are squaring that up to n, from I is equals to 1 up to n. So this is what we are going to do, and please note that we can still write this, okay? This summation here, we can write it in vector form and then write it as a product of row and column multiplication, because we know we can have our epsilon 1 up to epsilon n, and then this is also epsilon 1 up to epsilon n. So ideally, if we just do this column and row vector multiplication here, this row by this column, so what essentially we're going to have, you're going to have this and this epsilon 1 squared, then the next one is epsilon 2 squared, plus and so on to the product of this and this, which is epsilon n squared. So this is essentially what we have here. So we are going to write it as the product of these two vectors. But then we can see we are going to add the transpose here, because you can see that this is a column vector, and then we transpose it here to find the row vector. So this is the row multiplied with that column. This is what we are writing here. Okay? So this is the notation we are going to write here. This equals to that, and then equals to that. So it's a bit of some more substitution. This is going to be from I is equals to 1 up to n, and then this is going to be yi. Then we are going to see that the observed values, this is y hat, okay? Y hat representing, the values along this line of best fit, okay? This linear regression line here, okay? So that y hat, of course, we know it is a straight line, and we have given it by the equation of a straight line there, beta naught plus beta 1 x naught. So we shall we shall add the hat just to know that, just to show that it is the predicted values here. Okay, remember the difference. This is the predicted, but then the actual yi, we can say it is beta naught plus beta 1 x1 then plus the residues. Okay, so here we have yi minus beta naught, then minus beta 1 hat, and then we have xi. Okay, this is that, and then we are squaring everything. So the idea again, we want to minimize this. In other words, actually, we want to minimize the errors here. So in minimizing the errors, this is what we have come up with. We want to minimize that term there. So how do we minimize that term? We make use of our calculus here by saying if we want to minimize that term, then we are going to take the derivative, okay, the first derivative, and then equate it to 0, and then find the values for beta naught and beta 1, which for which this expression here is minimized. Okay, and then ideally someone could also take the second derivative test just to show that it is minimal, but I think, well, we won't do the second derivative test, just know that this is correct. However, if you so wish, you can also do the second derivative test. So right now we are going to proceed with the first derivative test. Okay, so what we are going to do is that we are going to take the derivative. Okay, so I just have to be clear with my notation here. Okay, so just a minute. So we are going to take your partial derivatives. Okay, so we are going to take the partial derivative, okay, first with respect to b naught, okay, and we are taking the partial derivative of epsilon hat transpose epsilon hat, okay, which is going to be the partial derivative with respect to b naught of then we can maybe write the whole summation term here, summation this, then yi minus beta naught hat minus beta 1 hat xi everything squared. Okay, so why the partial derivatives here? Because the two the variables for which we want to find here, we have beta naught, okay, and beta 1. So with regards to differentiations, these are going to be our two variables, okay. And then I think we should xi are constants because these are already known values that are given to us, okay, when we are collecting our data here. The xi's are the constants, they are the values which are given to us rather. And then the yi is a random what variable. Well, I don't want to go so much deep into that because I have to explain many things, but for now we can say our beta naught and the beta 1, okay, are the variables here with respect to differentiation. And then when we are dealing with maybe the statistics part and so on, the yi's are the random variables, and then the xi's are the constants, the values which we have, the data which we have collected. I hope that is clear. So we know if we are differentiating here, then we use what is that? The chain rule. Yes, we drop the power and so on and so on. But I'm not so sure. I think I have forgotten a negative somewhere. Okay, I just want to be sure. Okay, let's work it out. If it doesn't come out well, then maybe I shall go back and try to check. I'm not so sure. Alright, so the partial derivative here, so what do? We drop the power here. So we are differentiating with respect to beta naught, so we drop the power, then we will write our expression, okay, yi minus beta naught hat minus beta 1 hat xi, and then we multiply times the derivative of the derivative of what we have here, since we are differentiating with respect to beta naught, and the derivative of we are differentiating with respect to beta naught. So what would the derivative here of beta naught be? Negative 1, right? Yes. So I think that is why we have the negative here. Okay, now that's fine. And then we equate this to the 0. So, well, we have two unknowns. We have beta naught and then we have beta 1 in that equation. So I guess there is nothing much you can do to it. The next thing would be to find the partial derivative with respect to beta 1 of our squared residues here. So this is the partial derivative with respect to beta 1 hat of the summation from I is equals to 1 up to n of yi minus beta naught hat minus beta 1 hat xi then squared. As usual, we do like the previous one. We are going to drop the power, then we write the expression, okay, and then we multiply times the derivative of a beta 1. So the derivative of beta 1, we see it is going to be minus xi. So we have the minus here. Well, I can put the xi out of the bracket, out of the summation, but I can as well put it in the summation here. So Can I actually put it out of the summation? No, I cannot put it out of the summation, because with respect to the summation, we are summing over the index I. So the constant 2, the 2 is the constant. The 2 comes out, yeah, it's a constant. Whether I put it here or I put it outside there, it is okay, because it's the constant. And then, okay, also the negative, I can as well put it out, but the xi will have to remain inside the summation, because I am summing over the index I from I is equals to 1 up to n. The xi's are the observations, okay? Yes, so again, this we equate to 0, and then we solve these two equations here. So we have here equation 1, and then we have equation 2, which we are going to solve. Okay, so how do we solve this? A little bit of algebra here, and then see what we can cancel out. For starters, the 2 and the negative can cancel, the 2 and the negative, because we're equating everything here to 0. Okay, so from equation 1, we have that the summation. So we are summing from I is equals to 1 up to n. So for the purposes of time, I'm not repeating myself, I will just leave the indices out for now. So I shall just write that, but I'll add the index here equals to 0. And then the next one, we have the summation yi minus beta naught, then minus beta 1, now xi equals to 0. So maybe from the first equation we can find the expression for beta naught, and then we substitute it in the next. Okay, so okay, so we can separate this, the summation. We can say now we can expand that, not as such separating. So minus summation beta naught hat minus the summation beta 1, there's a hat here, beta 1 hat xi equals to 0. Okay, now remember, so what can we write here? Since we want this, I will leave this one here, negative summation beta naught hat equals to negative summation yi plus the summation of beta 1 hat xi. Okay, so with regard to differentiation, we said beta naught was the variable, but then with regards to the summation, it is a constant. Okay, so ideally, if you sum from I is equals to 1 up to n, okay, of a constant, then you're going to get n times that constant. If I sum from I is equals to 1 up to n 5, then we are going to sum this 5n times. Okay, so ideally it's just going to be 5 times n. So that is why here we are going to write n times beta naught hat. Okay, and then this one here, since we are summing over the index we are summing over the index I, so we can as well leave it as it is. And then we have the negative here. Okay, we can get rid of the negatives as well, since this is a negative, so we can divide through by a negative. That will become a positive, and then this one here will become a positive, and then this one here will become a negative. Okay, so we have a negative here, and then this one remains as it is. Okay, we can sum from I is equals to 1 up to n. This is the index over which we are summing, but then with regards to summation, beta 1 is again a constant, so we can pull this one out here. Okay, then next we can divide through by n such that we have beta naught. That is going to be equal to summation from I is equals to 1 up to n of yi divided by n, then minus beta 1 summation from I is equals to 1 up to n of xi divided by n. By definition, we know that this is going to be our y bar. Okay, this is our y bar, because if you sum all these values and then you divide by the number, you're just getting the average. So we have our y bar, and then what do we have here? Beta 1 hat. I make many mistakes, so please try to follow, or some notational errors. I keep on forgetting things here and then. So this is our beta 1 hat, and then again the summation from I is equals to 1 up to n of this xi divided by n is simply going to be x bar. Okay, write it well here. So this is beta 1 hat, and then this is our x bar, and then this is beta naught hat. Okay, still it's not much help, it's not helping us that much, because we still have beta 1 here in our expression. But then we can come from the second equation, and then from the second equation we just work it out the same way we have worked this one. So which one was the second equation? Yes, this is the second equation here. Was it? Oh, sorry. Why? You know, it's the same thing. I don't know what I was trying to do here. Okay. Where's the second equation? Yes, this one here. So we equate this one to 0. And then equating that one to 0, we are going to say we have the summation from I is equals to 1 up to n, which I'm not writing, of xi, and then we have our yi. We have our yi minus beta naught hat minus beta 1 hat xi. Okay, and then we are equating that to 0. So next, what do we do? We can substitute in. We have the value of beta naught, so we can say that yi, then the value of beta naught, we have y bar. This is a negative, so we have minus y bar, and then this is going to be a plus beta 1 hat x bar, and then we have now this other term here, minus beta 1 hat xi equals to 0. Okay. Alright, so how do we do this next? What is the best way to do? Oh, we have beta 1, we have these terms here which have beta 1 and beta 1, so we can just maybe say what we have, the summation, we have beta 1 hat x bar minus xi, and then on this other side we shall take the summation of whatever else remain. Oh, I think I have, it is multiplied by xi outside here. I should not forget that. Okay, we are multiplying it by xi. So and on the right hand side here, what do we have? The rest, which is xi. Then we have here yi minus y bar. I think, yes, that's it. Again, with regards to the summation, this and that will remain inside. I'll just write the xi there, I'll put it there, and then since we're about to finish, I can add the summations here, and then that is beta 1, and then we're summing from I equals to 1 up to n xi yi minus y bar. So from there we can say that our beta 1 hat is going to be equal to the summation from I is equals to 1 up to n xi to yi minus y bar, everything divided by the summation from I is equals to 1 up to n of xi into x bar minus xi. If I haven't made a mistake, that is the expression for which we have for beta 1. Okay, Of course, after getting the expression we have for beta 1 here, remember we have beta naught. We wrote beta naught hat as y bar minus beta 1 hat times x bar. So of course you come back here and in the expression for beta naught, where you have beta 1, you just replace it with this one here, okay, to get the expression for beta naught. Alright, now that is how we can compute the beta naught and the beta 1, okay. Remember, well, because you're given the values of xi, these the data we have, and then this is the observed. Yes, we are having the observed values here. For each xi, you have the corresponding yi, and then you can find the y bar is just the average of the yi's, and then this is still our xi, which we already have, and then you find the x bar as well. So the rest is just to punch in and punch in. However, there are a few other expressions which are commonly used, okay, so we shall look at those in a minute, okay. For instance, the expression you may see commonly used, beta 1 hat, is given as the summation of xi into y minus y bar. Then below, instead of having xi into x bar minus xi, we simply have the summation of xi minus x bar squared, okay. And then the equivalence is quite easy to find, okay. It should not be that hard. Oh, by the way, even this one here, it's not this. This is not the expression. That is slightly different. It is actually xi minus x bar instead of this, and then you have yi minus y bar. So if you want to find out that this expression here is exactly the same as this one here, all we need to do is to expand this. So a very quick expansion of that gives us okay, we shall do it here very quickly. Summation of xi minus x bar into yi minus y bar. We can say it is going to be the summation of xi into yi minus y bar, then minus the summation of x bar into yi minus y bar, okay. And we can still write this and say this is going to be the summation of xi into yi minus y bar, then minus, we can pull out the x bar because that is already a constant, okay. That is the average, okay. We already have a value for it and we can easily pull it out for now, okay. And so what else do we know here? We know actually that if you take the sum of these values here, if you take just this sum here, okay, if you take that sum there, the summation of each value here, and then you subtract the mean. If you take the summation of all this one is always 0. So that is why this is going to be 0, and then we are simply left with simply this first term here, and that is the equivalence yi minus y bar. And this is the term which appeared here. This one here. Okay, the xi into yi minus y bar. In a similar way, we can show that the denominator here, xi minus x bar squared, okay, should give us our original form which we had, which was summation of xi into xi minus x bar. So again, we expand this one here very quickly. So we have summation xi minus x bar into xi minus x bar. Then we write out summation of xi into xi minus x bar, then minus the summation of x bar into xi minus x bar. Okay, then we go through the usual again. We write this xi minus x bar, and then here we can pull out this x bar here because it is a constant. Okay, x bar summation xi minus x bar, and then again we know that this, let me use black, this sum here is a 0. Okay, and therefore we remain with only this, which is exactly what we have here. Okay, so yeah, so a slightly different notation which you can use and which is quite easy to memorize or even to remember is just this one, summation of xi minus x bar in times yi minus y bar, or divide by xi minus x bar squared, and then you sum up all these. Okay, good. So the rest, if we are given a set of values, xi's and so on, maybe let us look at our example here. Oh, where is my MATLAB here? Okay, so we have our values here. Okay, maybe not. Okay. Okay. Yes. We had our x values here. We had values in the first column. From our previous example, we had the values which represented, let me remember. Yeah, x was the pH of water, and that was in the first column, there. So I want all the rows of the first column, okay, and then I will suppress the output, and that was our pH, and then the concentration of the bicarbonate was the values of y. So we call this y, and then we are extracting the second column. Okay, so we have our x and then we have our y. So if you're given x and then you have values of x and then you have your values of y, and then they want you asked to calculate, okay, then you're simply going to write and then say, okay, I will calculate this linear regression. Okay, y hat this plus beta 1 hat xi. Okay, and how can you find your beta naught? Okay, first our beta 1. Okay, then we say that it is the summation from I is equals to 1 up to n of xi minus x bar into yi minus y bar divided by the summation from I is equals to 1 up to n of xi minus x bar squared. So we have everything. We have our values of x, we have our values of y. What else do we need? We compute x bar. How do we compute x bar? X bar is simply the summation of all xi's divided by n. Okay, so we have our x bar. So what are the? We have x minus x bar, and then x minus x bar, everything squared. Okay, we need also our value, our table of y. minus y bar, and then the product of x minus x bar times y minus y bar. Okay, so that at the end of it all, you will sum the values here to get this numerator, and then how do you get the denominator? You sum up all the values here so as to get the values will fit in the denominator here. Okay, and then you compute that, and then you compute b naught accordingly. So that is what you do. I don't know any other explanation I can give, but as usual, so since I'm the lazy person here, we shall just maybe, and these are 34 values. Okay, these are quite many, so we shall just compute them here. We shall just do an automated solution here, and then we also compare last time, because last time we did a scatter xy, and then we saw the regression. We drew the scatter plot. Okay, where is it? This one here. I'll maximize that, for which we then went ahead and drew the regression. Okay, where was that? Where is it? Is it on the tools? Yes. Basic fitting. Okay, it is linear. And then what else did we want? We wanted to plot the residues. I'm not so sure. Show the equation. Okay, and then we close. So we had that our beta naught was okay, is 4.3 times 10 to the power 2, which is 4.3 times 10 to the power 2 is what? 430. And then we had our beta 1, which is negative 38. Okay, beta 1 is negative 38, and then beta naught is 430 here. So let's see if we can compute them using our formula, and then we see if we can still get the values which MATLAB has also used here to plot. Okay, so in there, okay, we will refer to the notes. So we have our values of x, and then we have our values of y. So we need our x bar, so we shall call it x bar, and x bar is simply the mean of x, right? So we suppress that, and then we also get our y bar, which is simply the mean of y. Okay, so we suppress that. What else do we need in our expression? Okay, then the rest we can compute. So xi minus x bar, let us call it xx. Okay, so that is xi minus x bar, right? So it is going to be x, the column vector, and then from each value we are going to subtract the mean, which is x bar. All right. Similarly, yi minus y bar, let us call it yy, and then it is simply going to be y minus what we had as our y bar, and then we suppress the output. What else do we need? We need xi minus x bar squared. Okay, so last time I told you, so we are going to do xx square. Okay, so xx squared, we cannot just write xx to the power 2. Okay, for reasons I explained last time. That is going to give us an error, because remember xx is the column vector, and then also xx is the column vector, and then we know from your linear algebra you cannot, the dimensions here are not going to agree. But what we mean here by xi minus x bar then squared is like we are getting from each value where it is okay point wise. Actually it is here. They are saying that to perform element wise matrix powers we have to use this dot. Okay, that dot notation here, it's telling us that. So this is what we are going to tell MATLAB here, that we are going to get each value in that column and then we square it. Okay, now suppress the output and we have no error here. So that means that now we can compute our beta 1, and then we say our beta 1 is simply the sum of we are going to sum up here xx square, xx square, okay, and then we divide it by the sum. That is right, sum. Divide by the sum of xi. Okay, no, this is not right. This is what is supposed to be in the denominator here, xx square, and then in the numerator here it is the product xi minus x bar, then times yi minus y bar. So we should have, okay, we could have computed xi minus x bar, then, but we can do it here at once. Okay, so xi minus x bar is our xx, and then we are multiplying. Again, this multiplication is pointwise. Okay, so we are going to do that, and then we say, oh sorry, and then we, if for each value there pointwise, we are multiplying it by the value here in y, which is yi minus y bar. So if everything is correct there, yes, we should expect to get our beta 1, which is negative 37.7658, and let us see how it compares with the value here which we had. Yes, so almost, this is negative 38, and then this is negative 37, right? Okay, so similarly you can find the beta 1, I mean the beta naught. What is the beta naught? We call it beta naught, and then the beta naught, the expression was y bar. We already have y bar. Okay, minus beta 1 minus beta 1, and then we are multiplying beta 1 times x bar. Okay, so I think it's okay. Beta 1 is a constant, so when you multiply that constant, that is a scalar. In other words, when you multiply the scalar with this vector, it is, you know, yeah, the scalar multiplies times each element in the vector, and then this is a vector here, y bar. So is y bar a vector? Oh no, sorry, y bar. Oh, hold on, wait a minute. This, oh sorry, x bar. This is a scalar. Okay, y bar is a scalar, beta is a scalar, and then x bar is a scalar. Sorry about that. Okay, so everything is right, and that is 432. Again, if we compare it to our value here, this is 4.3 times 10 to the power 2, which is 430. Okay, so yeah, it's more or less the same, within the same limits. So yeah, so I'd like to end there, and that is how we find our beta naught and beta 1, which minimizes those error terms such that you know, the difference between our predicted and the observed values is minimum. Okay, all right, so thank you, and see you next time. All right, have a nice time. Bye bye.